So hi everyone, I'm André Ferreira and I'm going to be presenting to you today my master thesis on predictive medicine using interpretable recurrent neural networks. Let's start with a bit of motivation. So in machine learning, we've been watching to a trade-off between performance and interpretability. This is because we've been watching these new models of deep learning disrupting several fields with incredible results and even some new possibilities. These range from self-driving cars all the way to generative art, for instance. But these models' complexity makes them harder to interpret, which leads to a lack of trust in AI, especially in some critical use cases such as healthcare. Medics cannot afford to just blindly trust an algorithm, no matter how good it claims to be. And even in healthcare itself, there are some issues. For instance, the World Health Organization predicts that by 2030 there will be around 9.9 million global shortage of physicians. And even as of today, we already see a very high percentage of burnout in physicians. Just in Portugal, it's around 38%. So this leads me to think that healthcare could really benefit from AI. And to test this hypothesis, we need real-world data. So I've been using dataset from a local hospital in Lisbon, the Santa Maria Hospital, which features patients with ALS disease, in which we want to predict the use of non-invasive ventilation, a common treatment for this type of disease, over the next 90 days. After pre-processing the dataset, we got to 840 patients and to 46 features, which range from demographics all the way to neurophysiological tests. And so, having this, how can we facilitate AI in healthcare? Well, I really enjoyed this diagram from Christoph Molnar, which shows the main steps required for a successful machine learning project. And well, we already have the data part, so we can just focus on the three core pillars, like I like to call them the performance, the interpretability, and the usability. We'll go through each one individually, but let's first start with a bit of context. So, since we're using multivariate time series data, it's a good fit to use recurrent neural networks, and that's my main focus here on this thesis. And so, of course, they are good with this sequential data, but how do they actually work? So just as a reminder, for each timestamp t, a recurrent cell does the following. It updates its memory ht with the current input, it then can calculate an output y, and send the memory ht to the next identical cell. But there are some issues with these networks, because especially if we have long sequences, there is this trouble when we backpropagate the error through the layers. Because you see, there is this repeated multiplication over and over again with the same matrix W when we backpropagate through the past cells. So what happens here is that if that W matrix norm is less than 1, the gradient will vanish to 0 and the weights don't update properly. On the contrary, if the norm is bigger than 1, the gradient explodes to infinity and the model will just crash. Fortunately, there is this alternative approach of using long short-term memory models, which reduce these gradient risks by adding another memory vector, C, which essentially does just some pointwise operations instead of this repeated scaling by the same value. Well, both of these models can have some variations. For instance, we can make them be bidirectional, in the sense that the data and the memory of the model always also goes on the opposite direction, from the present to the past. And we can also include embedding layers. These are essential for these models because it can convert these categorical values, which aren't really directly handled by the models, and convert them to numerical vectors. And well, there is still one piece of information missing from both of these models. At least they don't really directly address the information of elapsed time between samples. This can be relevant as, for instance, we can have patients with varying sampling rates, for instance, being more data collected when they are in intensive care, or perhaps when they are with more light symptoms, just go momentarily to clinical visits. And well, since we have this missing piece, we can define the models that address this problem as time-aware models. And I propose 4 different solutions for this. We can either just add the elapsed time as a feature and hope that the model learns how to handle this information, or intrinsically take this information into account right inside the recurrent cell. There are, for instance, these examples of including a scaling factor inside the forget gate, or including as a parametric weighting inside the forget gate, or doing all of the calculations without interfering with the rest of the LSTM gates. And of course, there's interpretability. We already addressed in the beginning that it can be highly desirable, but what exactly is interpretability? Well, I like to define it at the same way that Tim Miller does, that interpretability is the degree to which a human can understand the cause of a decision. Knowing this definition, we can start with simple approaches, and a simple approach is just to use simple models, those that are simple enough to be straightforward to understand, such as decision trees. Decision trees really show a very reasonable logic process which we can clearly analyze and understand how it works. Or a linear regression model in which its own weights already tell us clearly how each feature impacts the output. We can also take a complex model, such as a neural network, and distill its knowledge towards simpler models. Or if we really want to use this complex model, we can also include an attention layer inside the neural network, which can give us an idea of how much the model looked at each feature. And well, these are all intuitive approaches, but they of course have some issues. For instance, when we need to constrain the model architecture, it can also limit the model's performance. And attention weights, well, they are an initial step towards interpretability, but they give an incomplete interpretation, because they only tell us how much the model looked at each feature, not how it actually contributed to the output. Fortunately, there are alternative techniques, such as perturbation-based methods. These only take small variations in the input and see how that affects the output. And so this way, it doesn't require a specific type of model. And inside of these techniques, there is SHAP. SHAP is an interpretability package which revolves around the game theory concept from the 50s, and it tries to unify several other techniques into the same core logic, to learn a simpler interpreter model from the original one through a local linear model, similar to the linear regression model that we saw before. And well, this is the linear models, the interpreter models equation. We have the interpreter model G, we have M features, an average output of that model, and the contribution scores of each feature I. In this case, we can also call them SHAP values. Notice here just that we're using slightly different feature representation, because what we do here is we try to do a local approximation of the original model around each sample X, but in a representation of X hat. This representation corresponds to binary values that indicate whether or not the feature is present. And by present I mean if we really use the original feature value, or if we just replace it with a randomly sampled one from a background set. For instance, if we were to use this original sample X, it would just translate to only features of ones. But if we replace some of those feature values with randomly sampled ones, the randomly sampled ones will get a value of 0 in the new representation of the hat. And well, thanks to the game theory foundations of SHAP, it has several desirable properties, but one that I'd like to highlight here is local accuracy. It indicates that the interpreter model will always try to match the original model's output, and in a higher level it also means that when we have an original sample X, the sum of SHAP values should really match the original model's output. And well, this is the core equation of SHAP. I know it may seem a bit scary at first, but we'll understand it step by step. So again, we have the SHAP value of feature I, the original model F for an input X, and this symbol corresponds to present features, and here we have the number of total features. We have the model output on the hat, and that same output without feature I. the first part of the equation corresponds to coalition weighting, that is, how much the subset of present features matters in this case. And the second part corresponds to the impact of feature I on the output from the current sample. And well, there are several ways to calculate SHAP. But the most relevant one here is really kernel SHAP, because it truly is model agnostic. It just relies on learning a local interpreter model based on this loss function, which has the square error between the original model and the interpreter, and the sample weighting that is similar to the equation that we saw before. This weighting scheme allows us to give a high value to either a very few or very large number of present features, and it also allows us to rank the samples by their importance so that we can train the interpreter model just on a subset of samples. And well, in here I show you a very simplified animation of how kernel SHAP works. What this indicates is that for each sample X, we will always learn a new interpreter model G, which will always try to match the output of the original model, and we will iteratively give new samples to train this model by iteratively hiding some of the features, which is equivalent to replacing the original feature values with ones from the background data. And well, with all of this you might be thinking, oh well, SHAP is so good, SHAP is so perfect, how can we possibly improve this further on? But well, hold your horses there, because of course there are some issues and some imperfections that we will address further on. So now, going back to the core pillars, let's start with the performance part. Of course, when we talk about the machine learning project, the performance will always entail learning a machine learning model that will aid us in the prediction task or whatever task that is we're trying to do. And well, we already addressed several concepts that could help us build this high performance model. So what I did here was to build a framework of a modular model that can contain several combinations of these concepts that we addressed. So let's check out how this model can be built. So first of all, we can have either one of 5 recurrent cells. We can use the traditional RNN, we can use an LSTM, or one of the intrinsically time-aware models that we discussed. We can also make it be bidirectional, or include an embedding layer, or even include elapsed time as a feature, as we addressed before. And well, with all of this, I trained literally all possible combinations of this modular model. And even so, I also trained each one of these combinations 3 different times with 3 different random seeds. This is just to try to reduce the luck factor from the model's initialization. And so, what we see here from the main results? We see right away that bidirectional LSTM models are on the top chart. They really lead the performance. We have this kind of surprise also that XGBoost, although it's not sequential model, it's got comparable results, at least comparable to unidirectional models. We also see, unfortunately, an unpleasant surprise that the intrinsically time-aware models had the worst performance. I suspect this might be because with their added parameters and the fact that we have a rather small dataset, perhaps it's not justifiable to use these models. And well, with all of these possible combinations, we can even do a brief analysis of the impact of each component of the model. And we see right away that bidirectionality is really the main contributor to the performance gains. We also confirm that LSTMs are better than RNNs, although in this use case it's not by much. The elapsed time as a feature does add something to the performance, but it's a very marginal improvement. And embedding layer, well, it barely interferes, and if it does something, it even worsens the performance in this case. Now going back to interpretability. We talked a lot about kernel SHAP and the fact that it made no assumptions about the model. But this can be a bad thing, because when we have certain special types of models such as RNN, they require a specific approach to it. For instance, if we were to apply kernel SHAP to an RNN model, we see that the sum of SHAP values does not always match the model's output. This breaks the local accuracy property that we talked about before. And so, why does this happen? What happens is that kernel SHAP will always try to explain each sample individually, with always considering as if each sample was a sequence of only one sample. So this eliminates the use of the model's memory. We can even confirm this by seeing that only the first sample in each sequence gets the right sum of SHAP values. So, what I have to do here is I dive deep into the kernel SHAP code and do some of the following changes. I added some parameters that allowed us to have a different behavior when we have RNN type models. I also made it go sequence by sequence in the interpretation instead of just sample by sample, so that we can do the main fix, which is to preserve the model's memory in each sequence. And so, doing this fix, we can see that the local accuracy property is valid again, as the sum of SHAP values always matches the model's output. But there's still one problem though, which is that SHAP is very slow. And the main contributor to this slowness is that there is this iteration through multiple background samples. We can even see that if we were to just use 50 background samples, interpreting a model on this dataset would take around 27 hours. Fortunately, even SHAP shows us the solution for this through the marginal expectation formula. We see here that SHAP will always try to do the output on the present features as they are, but with the absent features it will try to get the expected value from them. But wait a minute, if we want the expected value from the absent features, can't we just use a single background reference value, which is the average value of those features? Well, of course we can, and it can be even facilitated with just doing a vector of all zeros if we normalize the data through z-scores. In this case, the data will get a mean of 0. Applying this custom SHAP package, we get these overall feature importance plots for this LSTM model and this XGBoost model. What we see here is that although they are not exactly equal, they have a similar distribution of most important features. In particularly, we see that there is just one or two dominant features which have much more importance than the other ones, and both of these plots contain the same dominant feature, 3R, a respiratory symptom. The rest of the features on the top are usually present in both plots, even if they have slightly different order. This would be even more evident if you were to see a bigger list of top features. And well, having the dataset in context, it's expected that respiratory and mobility symptoms have the highest influence in this prediction of non-invasive ventilation. And well, all of this custom SHAP code is available on GitHub for reproducibility purposes. Now, we already did this feature importance part, but we are in a multivariate time series context, so is this enough? Because, of course, we have features that we want to interpret, but these features are inside samples, which on their own belong to sequences. So we should also try to interpret the impact of each sample or each instance in time along the sequence's outputs. A natural approach to this is just to remove the instance that we want to interpret and see how that affects the final output. I call this the occlusion score, in which of course we take the final output of the sequence and then subtract the output without the instance that we're trying to interpret. Of course, there could be an alternative approach as well, because for instance in healthcare, a patient could start to do a new medication or perhaps have an aggravated symptom that has repercussions on the rest of the sequence. So I think that's also important to take into account the output variation that each instance brings. I call this, of course, the output variation score. But well, both of these scores can be relevant, so what I did here was to create an instance importance score that does a weighted sum of both of these scores. I also included a nonlinear activation in this score, just so it makes it easier to highlight the high magnitude scores. Now going to the last step, the usability. In my humble opinion, when we talk about AI in healthcare, I think we can address usability in two ways. By releasing coding packages that make it more reproducible and facilitate the implementation of these techniques, and also by creating dashboards that can really be used by medical staff in a real-world setting. In terms of coding packages, I released data utils. This includes most of the code that I used for this thesis, all the way from loading data to pre-processing it and training the models. I also released the model interpreter, which includes the calculations for the importance scores that we talked about and also some plots for it. Then I made this dashboard, which serves as a proof of concept of, well, a combination of all of the ideas that we talked about and how this could be implemented in real life. So we have this homepage with the main insights over several different fields, but we can then go into more detail in each page. For instance, we have the performance page, which gives an overview of the model that we chose, and it can even be easy to compare different models on their performance right away in this page. Then we have the dataset overview, which, as the name says, it's the main stats of the dataset that we selected. We also have the feature importance, which shows the aggregate feature importance scores that we already saw before, and we can even filter by features. Then we have the most important page, the detailed analysis. In this case, we can really see the data on all the patients, on all their time series and samples. For instance, we have this first plot which shows in each row a patient's time series, and each circle or each dot that you see here represents a sample of that time series. We also see that circles can have different colors. This is due to their instance importance score, in which case, for instance, this red dot corresponds to a high instance importance score or a high contribution to that sequence's final output, in which case the blue colors indicate the opposite. Then, when we selected a sample from this plot, we can go below and see more information. We have here on the left a kind of patient report, which shows the most important feature values on that patient's time series. We also have the feature importance plot for the currently selected sample. And on the right, we have the final patient's outcome and the final output of the model. We can also go a step further and manually edit the current sample by changing the features all the way we want. And then we can see how that affects the final output of the model and also its interpretation. Now that we saw the dashboard, we can go to the conclusions and really see how we contributed to each core pillar. So what we saw is that LSTM-based models really are the top performing ones in the ones that were tested here. We saw that bidirectionality was a main contributor to the performance boosts. And in terms of interpretability, we adapted kernel SHAP to RNN-type models and introduced a new instance importance score. We also released 2 packages and created a dashboard as a proof of concept. Well, with all of these efforts in the core pillars, we achieved a solution of both trustworthy and high-performance AI applied to healthcare. In this use case in particular, we can even visualize and imagine a possible predictive medicine tool that could assist physicians, not replace them. Because, of course, we always need human doctors in the loop, but we can use AI-based tools to make their lives easier and their work more efficient. Perhaps go from automating some repetitive tasks all the way to interpreting complex cases and deriving new insights from it. In terms of future work, we could experiment with larger and more complex datasets. I even included some code to do distributed training. We could test potentially better models such as transformers and explore faster or more reliable interpretability techniques. Because of course, SHAP is still a bit slow, and it even has this unrealistic assumption of feature independence, which isn't really realistic. I also plan to present my work on scientific conferences. I've already been accepted at one, and I'm waiting for results on another one. And that's the end. Thank you so much for watching my master thesis, and I'll see you in the next one.